Okay, so let me begin. Okay. So first, let me explain the geometry again, because it might have caused some confusion last time. Okay, so you are talking about the bending of light. Okay. So the idea is that the stars are so far that we can think of starlight as parallel rays. Okay. And we observe it from somewhere here, right? So we receive light straight from the star, right? This is what we normally observe, and that tells us what is the star position in the sky. Right? You just extend it back and look at the star position. Okay. Now, when the sun comes close on the path, okay, the light bends, right? So each of these will bend a little. And so on. Okay. And then one of these basically reaches us. Okay. But the angle at which it will reach us, okay, will be different from the original angle, because it has bent by some amount on the process. Right? So this angle is delta phi. So if you extend it back, right, the original angle, right, if you call this 0, then the net angle at which it will reach us is delta phi, that we calculated last time. And this is what we experimentally observed. Okay, and this is what we compared with Einstein's theory, the result that we saw.
Starts to happen already. These times starts to curve some distance, not exactly at the point where the star is.
The star, of course, is very far. Right? This is the sun, which is coming in on the way.
Sorry, I meant the sun.
Yes, yeah, indeed. So once the sun is there, space-time is already curved, right? But if this line of sight is too far from the sun, right, then this curvature effect is small, right? So you don't see any bending, right? Of course, it always bends. So this effect becomes dominant only when the line of sight comes close to when the sun comes close to the path of the light, right? Because you remember that you have this factor of gm over rho 0, right? It was proportional to gm over rho 0, where rho 0 is the distance of closest approach. So unless rho 0 is small, right, this number is very small. Okay, so you need this to be small, to be big enough, right? We need this to be big, for observable effect. Is that clear? That's why this is important, right? That you have to observe the light when sun is more or less along the path. Okay, but normally you cannot observe it because the sun is too bright for the stars to be visible. Right? So it's only during an eclipse that you can observe it. Right? Otherwise, every time, I mean, if you could look towards the sun, right, any star that is in the path of the sun would appear as if its position has shifted in the sky.
Case of lensing, at the same time we will observe multiple images of the same.
Exactly, yeah. So lensing means that if you have a very massive object, right, then the light may come from two sides, bend in opposite direction, right, and then you will see lensing, right? But that in this case, I mean, the sun is not strong enough to cause that effect, right? I mean, there will be light rays which go below the sun, for example, will bend in the opposite direction, right? But that will not reach the earth. Because the bending is so little, right, that you will basically miss the earth, right? So the earth is only seeing a very narrow band, right, in this. So within that narrow band, right, it's always on one side of the sun, right? So you need strong enough bending so that on both it bends so much that the same point receives light from both sides, right? Otherwise, you will not see lensing. Is this clear? Right? I mean, if it's like this, right? One goes like this, the other one goes here, and if the earth is here, right, then you are not going to see anything, right? Or if the earth is here, you will only see one light ray, but not the one that is coming from the other side. Rho naught to be small. Yes, we need, yeah, this one thing should to be big. Is this okay? What can't be smaller? Yeah, exactly. We need that the experimental apparatus has some resolution of what angle it can resolve, right? So rho naught has to be sufficiently small so that this angle is big enough so that you can actually resolve it in the apparatus. Okay, so let me then start the next topic, okay, which is that we will still be outside this region of 2gm, right, where gravity is weak, but not so weak that we cannot observe any change from Newtonian gravity. Okay. So we'll consider bound orbits. I'm not completely sure. You can probably look up the net, right? The Eddington's experiment, for example, right? What angle they measured, right? And that, I mean, this GM, 2gm is about 3 kilometers, right? So from that, you can figure out how much rho naught should be, right? So in a sense, it was lucky that there is a visible star, right, which is behind the sun at that time. Okay, so let me remind you the equation that we had, right? We had an equation for d phi d rho, which was a constant k, square root of xi of rho, phi of rho, 1 minus 2gm over rho, and xi of rho, the inverse of this. K and n were constants of integration. K, n are constants. Okay, n is 0 for massless particle, and n is less than 0 for massive particle. Okay, that's what we are going to consider now for massive objects. But otherwise, we don't know what n and k are. They have to fix from that's just constants of integration. Okay, and we'll fix them. Okay. And the other equation that we had, right, the time dependence was d phi dt was k by rho square and psi of rho. Okay. So as long as psi of rho is non-zero, if rho is larger than 2gm, psi of rho is positive. Okay. And this means that d phi dt never vanishes. Okay. So it either remains always positive or it remains always negative. Right? So d phi dt either remains positive or negative. Or always negative. Okay, so phi either increases continuously with time or decreases continuously with time, right? The orbit just keeps moving in one direction. It never turns back. So what we are interested in is to find rho as a function of phi. Okay, we have a differential equation. So in principle, you can solve it to find rho as a function of phi. And in general, we'll be looking for solutions for bound orbits. Right? Bound orbit means that rho doesn't go to infinity. Right? So rho is bounded. So we expect that there should be a solution like this. Okay, so this is what we'll call rho plus, and this is what we'll call rho minus. Okay, in Newtonian gravity, you are familiar with orbits like this. There is a maximum distance from the sun and the minimum distance from the sun, right? That's the planetary, that's the how the planetary orbits look. Right? So the maximum rho and the minimum rho. And we expect that here also, okay, we'll have a form like this. What we are really after, of course, the whole shape of the trajectory is important, but what we will be trying to calculate is this quantity delta phi. In Newtonian gravity, delta phi is 2 pi. Okay. And that's the reason why the orbits are periodic, because it's saying that when rho comes back to its original value, right, from here to here, phi changes by 2 pi, right, which basically is no change because phi is a periodic coordinate. Okay. So if delta phi is 2 pi, then the orbits will be periodic, right? But if delta phi is anything other than 2 pi, then the orbits will not be periodic, right? Because when rho returns to its original value, delta phi has changed. Okay. So we'll try to calculate this delta phi, and the principle is clear. What you have to do is to integrate that equation, okay, between two successive values, right? Or we can just integrate from rho minus to rho plus and multiply by 2.
Or like if delta phi is not equal to 2 pi multiples, then it will be not bounded.
No, it will be bounded. It will be bounded. What is going to happen is that the orbit will start precessing. Well, I'm not a very good drawer probably. That the phi will, because by the time you have come back, the rho has come back to its the maximum, right? Phi has shifted a little, right? So the orbit will be bounded in the sense that the rho is not going to go up to infinity, right? But it will keep rotating. It could be, yes. In that case, it will be periodic, but it will be periodic with a much bigger period, right? It will keep rotating for a while, and then it will again come back to the original orbit. Yes.
Can come to rho plus and rho minus multiple, like oscillating circle.
Well, yeah, it can happen, but that means that the orbit will place in the opposite direction, right? If delta phi is larger than 2 pi, yeah, if delta phi is larger than 2 pi, then the orbit will move in the same direction as delta phi, right? The ellipse is rotating and the orbit will precess along that direction, right? If delta phi is less than 2 pi, then by the time rho has come back, right, phi has not changed totally, right? So then the precession will be in the opposite direction, right? So it will still be precessing, but precessing in a direction that is opposite to the motion of the planet, right? It just doesn't come, the pi doesn't come back all the way to 2 pi, right? Even when rho has come returned to its original minimum or maximum.
But it will be periodic. If it's rational, then it will be periodic.
If it's rational, it will be periodic, but with a much larger period than what we are familiar with, right? In Newtonian gravity, delta phi is just 2 pi. It will be closed, yes, exactly. Exactly. Yeah, if it's not rational, it will not be closed. Is this clear? Okay. So now basically we have to do some algebra, right? Otherwise the problem is straightforward. You have to just integrate that equation from rho minus to rho plus. Okay. And these objects, these will take as the input that will determine the constants of integration. Right? You have to determine the constants of integration somehow. Right? There are two constants of integration that is needed. Okay, because you have to fix n and k. Okay? And we will just take these rho minus and rho plus to be the input parameters. Right? For a planetary orbit, for example, we know what rho minus and rho plus are. Right? Using those, we will determine what these constants k and n are. So we have this equation that d rho d phi is 0 at rho equal to rho plus minus. Because that's where rho reaches the maximum or the minimum. Okay. So that means that that thing inside the that curly bracket, right, that has to be set equal to 0. Because d phi d rho has that to the minus half, so d rho d phi will have that to the plus half. So that has to be set equal to 0 because the rest of the terms are not 0 anyway, right? Because I of rho is positive, k is fixed. Well, k is just a constant. So we have two equations, n minus k square over rho plus square plus 1 over psi rho plus equal to 0, and n minus 1 over k square over rho minus square plus 1 over psi rho minus equal to 0. So first we can take the difference to eliminate n. Okay. That gives you k square into 1 over rho plus square minus 1 over rho minus square is equal to 1 over psi rho plus minus 1 over psi rho minus. So k square is, let me write it as rho minus minus rho plus okay. I have written it this way because rho minus is a smaller one, right? So 1 over rho minus square is positive, bigger than 1 over rho plus square. So the denominator becomes positive. That's why I have written it this way. And to determine n, we just multiply by rho plus square, the top equation, multiply this by rho minus square, and then take the difference. So that eliminates k square. So you get n times rho minus square minus, okay, this time it should be rho plus square minus rho minus square is equal to rho minus square okay. So this gives you n as rho minus square over psi rho minus okay, and you can easily convince yourself that this is negative. Okay, as it should be, because we are talking about a massive particle moving, right? Because well, for example, I mean, if we ignore the gm over rho term, right, then this psi rho minus and psi rho plus is just 1. Okay, and then n becomes just minus 1, right? Okay, so n negative is needed because we had seen that for massive particle n is always negative. Is this clear? Yeah, so we are basically using the fact that rho reaches its maximum or minimum at rho equal to rho plus minus. right? So if you look at the expression for d rho d phi, right, it will be the inverse of the whole thing, right? So that I have just put inverse of the whole thing has to vanish, right? But nothing else can vanish. So except that thing inside the bracket has to vanish. Right? That's why I wrote this. Are there other questions? So as I said, now it will be a bit of algebra. So we are going to substitute these in that expression. Okay. So we get d phi as k over rho square root of 0 d rho that's the n term, right? Then minus this is the k square over rho square term. This is the term I have written, k square over rho square, and then finally we have the plus 1 over psi rho. This whole thing raised to the power minus half. So we are going to analyze this, but we will use an approximation, right? The same kind of approximation that we did last time. Namely, we will assume that Gm over rho minus is small. Okay, I have written rho minus because rho is always larger than rho minus by construction, right? This implies that Gm over rho is small for all rho, for all the relevant rows. Gm over rho will be small. Why am I substituting? Oh, I can, but it's just that it will become longer, right? So because that k is just a constant, right? We are not going to integrate. We can put substitute at the very end. No, these are inside. There is rho dependence, right? Yeah. So you have to do the rho integral. Okay, that's why these. It's important that this part we analyze properly. But well, the point is this whole thing has to be raised to minus half, right? So the point is, so this part you have to analyze properly, right? To make the approximation. Here I can make the approximation at the very end. Okay, the 0 also you have to substitute at some point. Right? When we need, we'll do the substitution. But right now, I've just expanded out this curly bracket because this is the most complicated one, right? This is the one that you have to analyze first. Okay, so you assume this to be small, but we have to work to the first subleading order, right? Why first subleading order? That means that when we expand it, right, we keep the leading term in the expansion and the first subleading term, because we expect that the leading term will give the Newtonian answer, right? The Newtonian answer is 2 pi. Right? So leading term, if you just give the leading term, it's sort of much use, right? Will get recovered by the Newtonian answer. So to see the deviation from Newtonian answer, you have to keep at least the first subleading term. Okay. So you assume this to be small, but you keep up to the first subleading term. Is this point clear? So let's first try to see this curly bracket. Okay. What is the leading term in this curly bracket? Right? Because once you identify the leading term, you know what order you have to keep. Okay. If the leading term is of order 1, then we keep up to order gm over rho inside a curly bracket. If the leading term is of order gm over rho, then we keep up to order gm square over rho square. Right? So let's first try to understand what is the leading term in this expansion. Okay. So the leading term in this curly bracket, right? This is what we are trying to calculate. So the first term, right? We can, since you are interested in leading term, we can set psi equal to 1, right? Because psi is 1 minus 2 gm over rho, right? So you can set psi equal to 1. So we get minus 1 over rho minus square minus rho plus square times rho minus square minus rho plus square. In this term, because you are setting psi equal to 1, these are 0, right? Plus 0 or minus 0. And the last term is 1, because psi I have set equal to 1. So this gives you 0, because these cancel, right? So this gives you 0, which basically means that in this curly bracket, the leading term is 0, right? So to do the expansion, the first term is of order gm over rho. Okay, we'll see that first term doesn't cancel. Why is it? Because I just evaluated it here. Oh, because 1 over psi I am replacing by 1, right? So 1 over psi is just 1. These two just cancel. Inside the curly bracket, yes. Okay, so this says that inside the curly bracket, when you make the approximation, right, we have to keep at least up to order g square m square. Right? If the order gm term also vanishes, then you have to keep go one order higher. Right? But we cannot stop at gm, right? Because that will be the leading term, because the order 1 term is 0. Okay? So we'll now take this curly bracket and expand it up to order g square m square. Okay, so this means that need to expand well, suppose the gm term is non-zero, right? Then gm and g square m square will be good enough, right? We don't have to go to g cube m cube, because that will be our subleading order, right? So because you are only keeping terms up to subleading order, you have to keep up to g square m square. Is this clear? Exactly. Yeah. So then the next one will be gm over rho, right? And the next one will be gm over rho whole square. So up to that point you have to keep. Okay? That's what they say, right? See, if we didn't do this calculation, we would have said, okay, leading term is order 1, we just keep gm over rho. That should be good enough, right? But what we are saying is that is not good enough. No, we have not checked that that is non-zero. But if that is 0, then you have to go to gm cube over rho cube. Exactly. Because the leading term will be Newtonian result, right? So 2 non-vanishing terms inside this will need. Well, you don't need 2. I mean, as long as we have identified the first non-vanishing term, right? Then the next one is 0, it's okay. Right? Because there will be other terms which have that order, right? Xi to the rho also has gm over rho connection. But because this multiplies the whole thing, okay, here after you have factored out the leading term, you have to keep up to one for subleading term. Is this logic clear? Right? That this is something that multiplies the whole thing, right? This has 1 plus gm over rho, which is okay, right? But here, suppose you have gm and then g square m square, right? And we keep only up to the gm term, right? Then what you should have really done is that you have factored out the gm term, and then there will be 1 plus gm over rho term, right? That is of the same order as this one. Right? This is also 1 plus gm over rho. That will also be 1 plus gm over rho. That the factor gm over rho factoring out you have done anyway, right? That's the overall factor. So whenever you have a multiplicative term, right, then inside that you have to keep the leading term and the next one. Right? The leading term you have to identify. Right? If the leading term is 0, right, then the next order becomes the leading term. Right? That and the next one you have to keep. Is this clear? Right? I think when I do the calculation, maybe it will become a little clearer. Okay, so this is 0. So let's expand. So need to expand at least to order g square m square or gm over rho square. Okay, so let's do that. So this curly bracket becomes minus 1 over rho minus square minus rho plus square times rho minus square times 1 over psi. Let me remind you, psi of rho is 1 minus 2 gm over rho. Right? So you are trying to expand 1 over 1 minus x. That's the 1 plus x square. We can stop at x square for now. So 1 plus 2 gm over rho minus plus 4g square m square over rho minus square. And then minus the same thing. Then here you have 1 of minus 1 over rho minus square minus rho plus square. Sorry. And here again we have 1 plus 2 gm over rho minus and then 1 over psi rho, so plus 1 plus 2 gm over rho. Is this clear? Yeah, so this whole thing is the curly bracket. Oh, yeah, yeah, thank you. Now the first thing you can check, okay, which I'll not try to do is that the coefficient of 2gm doesn't vanish. Because this, for example, has 2gm times rho minus 2gm times rho plus. Okay, that these are no rho dependence. This is 1 over rho square. Right? This is also 1 over rho square. So the 2gm coefficient doesn't vanish, right? Which is good because you can stop at g square m square. Nevertheless, it looks like a complicated expression, right? But we are going to simplify it. We are going to simplify it by using two observations. Okay. One is that by construction, this is 0 at rho equal to rho plus and rho minus, because we determine this constants of integration by setting rho equal to rho plus and rho minus. Right? So this is 0 at rho equal to rho plus and rho minus. And then the other observation is that this, whatever has appeared there, is a quadratic function of 1 over rho. So the first observation is that this is 0 at rho equal to rho plus and rho minus. Second observation is that this is a quadratic function of 1 over rho. Right? These are of course constants. Rho plus and rho minus are just constants. Right? So the first term is just a constant. This one you can say has a 1 over rho square. Right? And this has 1 over rho and 1 over rho square. So it's a quadratic function of 1 over rho square, right? Which basically means that this must have the form a quadratic function, right, which vanishes at rho plus and rho minus, right, has this form. Right? This is just factorization of a quadratic polynomial. Okay. So you have to only find a, right? So you need to find a. And that is easy because you just have to identify 1 over rho square coefficient, right? So a multiplies 1 over rho square. So you just have to look for 1 over rho square coefficient from here. So 1 over rho square coefficient. So this should be equal to the coefficient of 1 over rho square. So that gives you a as, so first there is a 1 over rho square here. So minus times all that. Okay, so one term cancels. So 2gm, pardon, to the power, yeah, thank you. Plus, this closes here and then plus 4g square m square. That's our last term. So this we can calculate. We can factor out, this is just a square minus b square, right? So we can factor it. 1 over rho minus 1 over rho plus just cancels this term. So you get minus 2gm minus 4g square m square which is right? In the first term, I just factored it and cancelled out the 1 over rho minus 1 over rho plus space. Second term is just cancelled completely. And third term is there. So we have now determined A, right? So you know what this object is. Is it okay? So the idea now is that we are going to substitute this in this expression over here. Yes, which is 0, which is okay, right? The leading term is GM, right? So that basically means that this inside the curly bracket, the subleading part is 0, right? But there will be subleading parts from here, right? If you want to keep in the curly bracket, say G cube M cube, right? That will be about G square M square relative to leading term, right? Which is going too high because we already will get order GM term from that. There will still be some deviation, right? If we find that there is no deviation, that means that Einstein's gravity and Newton's gravity agrees to order GM over rho corrections, right? Then you have to go to next order, right? But we will see that already they will will find deviation at the first order, right? Because this certainly has GM over rho term. The expression for K also has some GM over rho correction, right? So all those will be taken into account. So what you are going to do is that just substitute whatever you have here in this expression. I think this part we don't need anymore. So this gives you d phi okay, let me write the expression for change. The change that you wanted to calculate. So I'll write as an integral. Half the, yeah, that's why I multiply by 2, right? So the total change will be twice this. So this part we determine to be okay. So now we have to simplify it. The way we will simplify it by we will change variable to x, which is 1 over rho. And we also define x plus minus as 1 over rho plus minus. And we use square root of 0 as 1 minus 2 GM. Xi was 1 over 1 minus 2 GM over rho, right? So square root of 0 is given by this. So that's 1 plus GM over rho. Okay. We have kept up to first subleading order. So that's 1 plus GMX. Okay, k we still keep as it is. We'll do it at the end. Okay, the expression for k. So is this okay? So this is going to make things simple, okay? Because now delta phi becomes 2 integral x minus to x plus times k dx. Pardon? Oh, I'm changing variable to rho equal to 1 over x, right? So in rho is rho minus, x is x minus. Because x plus minus also have defined as 1 over rho plus minus, right? So in rho is rho minus, x is x minus, right? And then rho is rho plus, x is x plus. Change of sign, yes, indeed, that's true. So it's x plus to x minus. Okay? Because you could have written from x minus to x plus, but then there will be a minus dx here. Right? Because x is, so dx is minus d over rho square.
X equal to 1 by rho is the circuit.
Yes.
Rho equal to rho minus, then a corresponding x is 1 by rho minus.
That's x minus. Yeah, right? Yeah. I have defined x plus minus as 1 over rho plus minus. Yeah. Is it okay? So let me write the whole thing. So this is square root of xi, you have determined 1 plus gmx. Okay. This one, let me write as 1 over rho minus plus 1 over rho plus over 2 gm to the power half. Okay. And then x minus x plus, the minus sign, so this part is just a constant I have factored out of this product. Okay. Pardon? Why am I? This one? Oh, I can, okay, yeah, I can do that. Let me simplify things a little bit. X minus plus x plus. So now it's getting towards more familiar kind of expression because this is quadratic in x, right? So you have to basically write it as a complete the square. Right? You can write it as by completing the square. And let me write the result anyway. Then you'll see if you agree. So this quantity I have x minus let's see if this is true or not. Okay. So minus x square, right? X square is there, x square. Right? Then the let's look at linear term in x. So linear term in x according to this is x times x plus plus x minus. Right? That is there, x times x minus and x times x plus, right? This minus sign cancels the minus sign over here. And then here you have minus x plus x minus. That comes from this square minus the x minus plus x plus by 2 whole square. Right? So this gives you minus 2x minus x plus. This gives you 2x minus x plus, right? The difference is -4, and then there's 1/4 sitting here. Okay. So now it's clear what change of variable you have to make, right? So we change variable again, variable to u, namely x minus x plus plus x minus by 2 is x minus minus x plus by 2 sin u. Notice that this is positive. X minus minus x plus is positive because rho minus was less than rho plus, right? So x minus is larger than x plus. The other thing is that because this is sitting inside a square root, okay, this quantity better be positive, right? Which means that this one better be less than this. Right? And that basically follows from the fact that x is between x minus and x plus. You can check that as long as x remains between x minus and x plus, this is smaller than this. Okay, so if you make this substitution, okay, let's look at the limits. So x equal to x minus, this becomes x minus minus x plus by 2. This gives you sin u equal to 1. That's u equal to pi by 2. And x equal to x plus gives you sin u equal to minus 1. That's u equal to minus pi by 2. Right? So in terms of this u variable, we have to integrate from minus pi by 2 to plus pi by 2. Yeah, because we are trying to calculate the first subleading order, right? So if you expand it to second order, right, you'll get 1 plus gm over rho plus g square m square over rho square, right? There, the g square over m square over rho square will contribute at the subleading order. See, it's like this. That imagine, okay, let me explain this here. Suppose you have a small number epsilon, right? Which is in our case is gm over rho. Okay. And imagine that you have a term like 1 plus epsilon, 1 plus a epsilon plus b epsilon square plus higher order, doesn't matter. And then somewhere here we have c epsilon plus d epsilon squared plus c epsilon cube to the power minus half. To get first subleading order in epsilon, here you have to keep the d epsilon square term, right? But not here, because because let's see how it will work. So it will give you c epsilon to the minus half times 1 plus d over c epsilon plus e over c epsilon square to the minus half, and then 1 plus a epsilon plus b epsilon square, etc. Okay, so this gives you c epsilon to the minus half, and then 1 plus 1 minus b over 2 c epsilon plus order epsilon square, and then this gives you 1 plus a epsilon plus order epsilon square. So when you take the product, right, this product becomes, so this becomes c epsilon to the minus half times 1 minus d over 2c epsilon plus a epsilon plus order epsilon square. Is this manipulation clear? Right. So what we see is that to get order epsilon correction, right, we have to keep d term, right, which in this language corresponds to order epsilon square term, right, because the leading term was c epsilon. But here we don't need the b, right, because b would have contributed at higher order, right. This is in the order epsilon square term over here. Is this clear? No, first subleading order, right? So if you wanted second order, right, you have to keep the order epsilon q. This e epsilon q will also be needed, right? So you see that here you will get a, after you have factored out the epsilon, right, we need to keep the e epsilon square, right? That we have not done. Right? So the goal is to go to the first subleading order, right, which means that the leading order, after you have factored out everything, the leading order will give you something, and then the next order is what you want to calculate. Okay. So that's why given when you have a product of factors, right, then for each factor you have to check what is the leading term, and then depending on that you have to decide how many terms you want to keep. Okay, and that's what I have done here, because here, because the leading term was already 1, right, I didn't have to go up to g square m square. Is this clear? Okay, so let's try to write this delta phi expression. Maybe I'll erase this, I think. Yes. So rho was from rho minus to rho plus. So if you had written d rho, it will be 1 over x plus to 1 over x minus. Right? That's the limit of on rho. Right? Because rho was from rho minus to rho plus. Right? Rho minus is just 1 over x minus. Right? So in terms of rho, it is from 1 over x minus to 1 over x plus. But you are writing the integral over x. Right? So x is 1 over rho, right? That's why it becomes from x plus to x minus. So delta phi is 2 integral from x plus to x minus e. So dx now becomes right because of this change of variable. Then 1 plus gmx I keep as it is. And that one I keep as it is. Half, thank you. Yeah, it will get cancelled eventually. Right, but let's just keep things as it is. So here you will get a factor, see x, this we have substituted as x minus minus x plus by 2 times sin a, right? Okay. So these give a, so x minus minus x plus by 2 whole square comes out, right? There's a minus half, so it gets raised to minus half, and then you have 1 minus sin square a. That's cos a, right, in the denominator. So you get x minus minus x plus by 2 to the power minus 1 right? Because there's a square and then it's raised to minus half, minus 1, and then 1 over cos e. Right? Because once you have made this substitution, okay, you get 1 minus sine square e. Right? That's cos square you raised to minus half, that's 1 over cos e. Is this clear? Okay, so now we are getting towards the final result. Oh, here also I should substitute. I should have done this. Let me do this. I'll write it here. It was x, right? So for x, I write x plus x minus by 2 plus also multiplied by gm. Yes, clear? So this part just came from this 1 plus gmx. Okay, this is basically 1 plus gmx. So now you can see there are several cancellations. So first of all, this one cancels. Cos u cancels. So the only u dependence is here. I know this I should have changed the limits from minus pi by 2 to pi by 2. That's what we saw here, right? The limits become u equal to minus pi by 2 to pi by 2. Is it okay? Other questions? Okay, so I just change variable from x to u, right? Change the limits appropriately over u. And now you see that the only u dependence of the integrand is here. Right? Rest of the terms don't depend on u. Right? And minus pi by 2 to pi by 2 sine u du is just 0. Right? So this term drops out. For the rest, the u integral just gives you pi. Right? Minus pi by 2 to pi by 2 du is pi. Okay. So you get 2 pi times k times x minus plus x plus over 2 gm to the power half. 4 pi? Yeah, 2, because this is given pi, right? So, and then the factor of 2. Okay, so finally we need to substitute for k. Okay, so let's now, I think I can now erase everything from that side. Is this clear? Are there questions on this? Yes. That's right, yeah.
So I can't, if this is, would that happen that those paths would be equal?
That you can check because it's the same integral that you are doing, right? From rho minus to rho plus versus rho plus to rho minus, because the integrand is only a function of rho. Exactly, the form of the integrand remains the same. Okay, so now let me write down the expression for K. Okay. I'll write in terms of x plus and x minus. Okay, if you go back to your notes, right, let me remind you what K was. Yeah, K squared. K squared was, sorry, yes. So this is 1 over x minus square minus x plus square. Okay, that's the definition that we have given. And here we get 1 plus 2gm over rho minus, that's 2gm x minus plus 4g square m square x minus square, and then minus 1 minus 2gm x plus minus 4g square m square x plus square. Okay, so this part then gives you 2gm x minus minus x plus 4g square m square okay, so you can factor out x minus minus x plus, so you get 1 over x minus minus x plus, sorry, x minus plus x plus, and inside 2gm plus 4g square m square okay, that's 2gm should have this coefficient, right? So I just cancelled the x minus minus x plus, right, from here, right, because this factors into x minus minus x plus times x minus plus x plus. Okay? So I kept the x minus plus x plus, and then I cancelled off the x minus minus x plus. Pardon? Yeah, but this is there's square root, right? So this is k square. Right? So k is the square root of this, which is square root of 2gm times 1 plus gm over, sorry, 1 plus gm times x minus The order g square m square term we are ignoring anywhere. Okay, so let's now substitute this expression for k here. So this gives you 2 pi. K is square root of 2 gm times 1 plus and then the rest. This is okay. Okay, and now you see that some more cancellation happens because this term can these two terms cancel. And this product you can combine. So let me write this here. So this is 2 pi times 1 plus 3 by 2 gm Is it clear? So you first of all see that the leading term is 2 pi. And this is what you expect from Newtonian gravity. This is the correction. This correction is what represents the amount of precision of the orbit. Right? Every time you have an orbit, right, it rotates by this amount, right? So precision, that means is 3 pi gm times 1 over rho minus plus 1 over rho plus. And this of course adds, right? So even if this number is very small, if you follow the orbit over large time, right, this will add because every time you have an orbit, it precises by that amount, right? And the same sign persists, so it keeps adding. So by observing an orbit over a long period, right, you can figure out how much is the precision and compare with what it predicts. And this was observed in Mercury, right? Because that's the closest. Right? You see that the amount of precision depends on this ratio gm over rho. Right? So the smaller rho is, the larger is this effect. Right? So clearly the orbits which are closest to the sun will have the most effect. Right? So this was observed in Mercury. Right? In fact, it was observed before general relativity. General relativity explained why the orbit precises. Are there questions? Well, yeah, if this happens to be rational, then yes, but the part is, see, rho plus and rho minus are just random numbers, right? The planets just got stuck, and a random number being rational is a set of measure 0. Right? So most orbits are not periodic. Let me put it this way. The set of orbits which are periodic, right, are a set of measure 0 among all the orbits. It doesn't rule it out, yes. Right? We have to make an infinite fine tuning of initial conditions to get periodic orbits. Yeah, then you have to worry about higher order terms, right? It is true that, I mean, under a very, very special circumstances, you may get periodic orbits, but a generic orbit is not periodic. I mean, one simple case is circular orbit, right? If rho minus and rho plus are equal, then obviously the orbit will be periodic, right? Phi is not, rho is not changing at all. Yeah, so this shows that it is in the positive phi direction. It's a consequence of general relativity. It could be, yeah, there may be negative terms and at higher order, right? But then you have to go to sufficiently close so that the higher order terms are as big as this term, right? Then the approximation itself breaks down. See, if the higher order term cancels this term, right? Then that means the approximation is valid, not valid. Then I have to do an exact calculation. Right? This says nothing about what happens under higher order corrections. But as long as this is small, we expect the higher order corrections to be small. Okay? So that's not going to change the sign of this term.
Does the circular orbit satisfy?
Yes, circular orbit does. Circular orbit, nothing is changing, right? I mean, the phi is only changing, rho is not changing. It does, yeah. By symmetry, you can also check, right? That if you set, I mean, for circular orbit, right? That's this bracket inside is just identically 0, right? You said rho plus equal to rho minus, and that will be satisfying the equation. Exactly. So circular orbit is a set of measure 0, right? In all the orbits. And that's why the orbits are elliptical, right? Typically. What do we measure 0? Set of measure 0 means that if you pick a condition at random, right, you will not get circular orbit. On a real line, right, if you pick a point at random, the chance that it will be an integer is 0, right? The chance that it will be a rational number is also 0, because rational numbers form a set of measure 0, right? So in this sense, if you pick a random orbit, right, then rho plus and rho minus are just real numbers. Right? For circular orbit, you need rho plus and rho minus to be equal. Okay? That's a set of measure 0 among all the initial conditions. Right? So that's what one means by set of measure 0. That it's that conditions, initial conditions picked at random will not give a circular orbit. No, see, here the Riemann is not 0. There is curvature in space. Nevertheless, a circular orbit is a solution to the equations. Right? Because Riemann tensor is certainly not 0. You can calculate the Riemann tensor for a Schwarzschild metric, right? And it is certainly not 0. Scalar curvature is 0 because we have solved the equation R mu nu equal to 0, right? So outside a region where there is mass, scalar curvature is always 0. Exactly. So the probability of finding a circular orbit, right, or a rational orbit is 0. Any other question?
Yeah, this confusion. This final formula of precision. There is a circular orbit. We can apply this formula to that.
Well, circular, no, the analysis that we did doesn't really hold for circular orbit. Circular orbit is special. You can do the calculation very easily, right? Because as I said, for circular orbit, 0 d phi is 0. Right? That just corresponds to setting n equal to that the thing inside the square bracket inside the curly bracket equal to 0. Right? So circular orbit is special. That doesn't follow this analysis. Exactly. D phi 0 will blow up, right? That's the equation we have solved. So for that, you just go back to the original equation, right, and simply set rho equal to constant, right, 0 d phi equal to 0. So that doesn't even that's not even a differential equation, right? That basically will determine n and k in terms of rho, with the value of rho for which it's circulating. Any other question? Okay, so these three are the classic tests of general relativity, right, that we discussed. One is the time delay. Okay, that if you have that doesn't require Einstein's equation, right? That's just a equivalence principle. Okay, and then these two, bending of light and the precision of the orbit of Mercury. I think the amount of precision was some 43 arc second per century or something. It's a very, very small precision, but apparently astronomers have been observing the orbit of Mercury for a long time, right? So that's why I said that this adds, right? So you don't have to look at just one precision and then how much orbit has changed, right? You observe over a very, very long time. And then from there you can calculate how much is the precision per orbit, per revolution. And you can compare. But I should say that this is the general relativity is not the only effect, right? Because there are other effects of which causes precision, just the perturbation due to the other planets, right? Because those you ignore when you do Newtonian gravity, right? But even with the Newtonian gravity, the perturbation of the other orbits causes precision. But what people have found that after taking into account all of those, right, the Newtonian gravity effects, there is still some effect which couldn't be explained, right? And then this explained that effect. Whatever is not explained by Newtonian gravity. Okay, so our next topic will be to study what happens when you go inside the R equal to rho equal to 2gm. Okay, because so far we have assumed that rho over 2gm is small. Okay, so that 2gm over rho is small. Okay, but now we want to understand what happens when you actually go towards rho equal to 2gm. So let me at least begin the discussion and then we'll continue tomorrow.
Situations, like, for example, here we discussed the precision. Other than that, this planet's orbit is going out of bound. Like here, we are assuming it to be always within rho minus and rho plus.
Yes.
If there are situations like it is going beyond this limit,
I think for a two-body problem, it will not happen, right? For many body problem, it may happen that the orbit they look like bound orbits, but suddenly one of the orbits just go out. See, this is even in Newtonian gravity, right? It may happen that because the many body problem in Newtonian gravity is not solved, right? So it could happen that the total energy, of course, has to be conserved, right? But somehow the planets exchange energy, and one planet gets kicked off the bound orbit.
in this two-body problem situation,
No, in two-body problem it will not happen, right? Even in Einstein's theory, right? Within two-body problem it will not happen, right? What will happen for the two-body problem? That if you assume, okay, see here you have taken the suns to be static, right? But eventually, even that just a two-body problem requires doing two-body analysis, right? Because you have to look at the effect of the first body over the second one and the second one over the first one. This problem can be mapped to an exactly one-body problem in Newtonian mechanics by going to the change in center of mass and the relative variable, right? This doesn't happen in Einstein's gravity. Okay? So the two-body problem also is not solvable in Einstein's gravity. But what we can argue on general grounds, right? That if you have a two-body problem like this, then the orbit will keep radiating gravitational radiation. Okay, which we'll study later. But just like a charged particle moving around each other, right, radiates electromagnetic radiation. Right, this orbit will keep radiating gravitational radiation. Right, that is very small, but nevertheless there will be gravitational radiation, okay? And that will make the orbits collapse eventually. Yeah, it can be extended to many body also. Any more than one body system in gravitational physics will typically radiate gravitational radiation. Yeah, so bound objects don't fly off, right? Two-body problem in gravity, right? You can show that they don't fly off, but they can collapse by emitting gravitational radiation. Yeah, indeed, but not two-body problem. Multi-body problem, yes, it will happen. Sorry, was there a question? Yes.
This equation that we are solving, we solve in the frame of reference of the matter. The rho that we have defined.
Yes. We're assuming that one body is very heavy, right? So that it doesn't get back reacted.
Even if we don't assume that body to be heavy, it's still in the frame of reference of that body.
Yes.
And then we are determining the geodesic equation.
That's right. Yes.
How is it two-body problem?
No. So we have not solved two-body problem. Oh, you are asking that whether you could go to the frame of reference of that body. Right? See, if you go to the frame of reference of that body, even then, right, when you write down the full set of equations, there will be an effect of the other body on that. Right? It's true even in Newtonian gravity, right? You could have said the same thing for Newtonian gravity. You go to the frame of reference of that, right? But we know that there is an effect of the other body because you have to use a reduced mass, right? I mean, in Newtonian gravity, you can map the problem to a one-body problem by introducing a reduced mass, right? But still, it's not that you can totally ignore the effect of the motion of that body. Okay? And that same thing happens in general relativity.
Gravity, if the energy of the orbiting body, if it's more than certain limit, it will be the orbits will be unbounded.
Yes, exactly.
In this case also this.
Yeah. In this case also this will happen because you have assumed bound orbit, right? Because you assume that rho is between rho plus and rho minus, right? So certainly here that can be objects which fly past, right? Which are not bound objects. Right? There also the actual trajectory will be somewhat different from what Newtonian gravity predicts. Right? Even the trajectory of light is different, right? So certainly, I mean, you can have unbound orbit, but you can take into account general relativistic effects. Any other question? Okay, so let me just then say what we will do, right? I'll not write any equation. So the first task will be to argue that this singularity, apparent singularity at rho equal to 2gm is a coordinate singularity. Okay? And we'll do that by simply writing down a new coordinate system. Right? We'll write down a new coordinate system. We'll give the change of variables. Okay? And in the new coordinate system, we'll see that the metric when you write in the new coordinate system, it's not singular at rho equal to 2gm. Right? It is still singular at rho equal to 0, but it's not singular at rho equal to 2gm. So then we can use the new coordinate system and study what the geometry looks like, right? What will happen if you now take a point particle, right, and follow the geodesic in that new coordinate system. Okay, so that will be the strategy, that we have to first find a coordinate transformation that makes the metric non-singular, and then study the motion of particles in that coordinate system. Right? Fortunately, we will see that the second part is much easier in that new coordinate system that we'll be using. Right? We don't have to actually solve equations, right, to get a general idea of what happens to a particle that goes inside this rho equal to 2gm. Right? We will be able to do that. Conclude that without doing much calculation. Okay, so I think maybe we will continue tomorrow with this. Limit on the
propagation of the curvature, because there should be some relativistic limit.
Yeah. So it will be the speed of light.
Okay.
Yeah. So the gravitational radiation, right, will propagate at the speed of light.
So have we seen it so far? Like
no, we'll discuss gravitational radiation afterwards.
Is it okay to develop our analysis without imposing that limit, since we are looking for a relativistic theory?
I think the point is this analysis is valid when one body is very heavy, right? But if that's not the case, then you have to take into account the effect of gravity. See, here you have to assume that there is no back reaction, right? The gravitational effect will come when you take into account the gravitational field of the body which is rotating. Right? Here you are pretending as if the body which is rotating is a test particle. right? It doesn't affect gravitational background gravitational physics. So that under that approximation, this is valid. Right? But once you take into account the finite masses of the bodies, then you have to take into account also gravitational radiation.
I was trying to ask in a general case when we introduced Riemannian geometry and right we wrote things down different things we wrote down. So I couldn't really see the limit of C being imposed on the curvature for the Riemanns and we were writing, or maybe it's simplicity somewhere.
No, that we will not see because so far you have not studied propagation.
I see.
Right? When you study propagation of signal, then you will see that limit.
So we imagine the mass has been put and whatever geometry we get, we just take it and do things.
Exactly, that's right.
So we are not putting the mass and then observing what happens slowly and slowly.
Yeah, the point if you try to move this mass, right?
Yeah, exactly.
Then the fact that that effect will be felt sometime later, right? That will
So something like this you
exactly, because so far you have not moved that mass at all, right? So just assume that the mass is given to us, and then you are studying the propagation of a particle in that.
One body problem and one body problem.
Yes.
So in this case, we are doing a one body problem because the sun is at rest and the planets are only moving.
Exactly.
And the mass which is coming to be something equivalent to the reduced mass of the Newtonian mechanics. Is that so?
Well, right now the approximation that we have made is that the mass of the planet is much smaller than the mass of the sun. So the reduced mass is the same as the mass of the planet, right? So you have not seen the approximation in which you actually have to use reduced mass, because then other effects will come in, right? So the approximation that we have made so far, we have just simply assumed that the mass of the particle which is moving is much smaller than the mass of the static particle.
So you're saying when it will become a two-body problem when we take into account the other guys, the larger, for example, the sun's motion also into account.
Exactly, that's
Then,
right.
Then it will be.
Yeah.
And whatever the delta phi we calculated over here, that will be like observer independent. For example, if one guy measures from Earth or from somewhere.
Yeah, you can actually present it as number of revolutions, right? That per revolution, how much is the change in the angle,
Okay.
right? Or you can say how many revolutions does it take for the orbit to return to its original position, right? So stated that way, it's sort of coordinate dependent statement, right? So that's certainly observer independent. Yes, so instead of stating how much is the change in the angle, right? You can do it this way: that how many revolutions it will take for the orbit to return to its original position, right? Or approximately return to its original position.
And what do you talk about the gravitational radiation when the EW will come into account in these cases? For example, so far we haven't seen anything.
Yeah, if you take into account the finite mass of the particle that is moving, right? Then the gravitational wave effects will come in. Right? It's like in electrostatics or even in electrodynamics, right? When you talk about particle motion, charge particle motion, as long as the charge carried by the particle is small, the electromagnetic radiation is small, right? But when the charge becomes large enough, then the electromagnetic radiation effect takes place.